Good afternoon, ladies and gentlemen. Thank you for the opportunity to tell you about OC Technologies' new HISAOR chip. HISAOR comes from two Irish language words that mean artificial intelligence, which probably gives the game away a little bit. A few years ago, it became fairly obvious that the satellites of the future would need to be able to do significant image processing and other intense computational work on board, which implied they would need neural network processing capabilities. So a project was started to produce a chip that would do that while being suitable for use on a satellite through having good resistance capability, good resistance to radiation, low power consumption, and so on, while providing the maximum possible throughput and providing the maximum connectivity to different kinds of devices. That was a few years ago. And a few months ago, the chip arrived, and here it is. And as you can see, at a glance, well, it's a chip. Internally, it has a central spine, which basically are the three main computing engines or areas within it. The bottom one to do with processing media input from cameras and so on. The middle lot in green to do with neural network processing. And then the main processors up here, which look after the house and do a lot of the control of the rest of the system. There are a lot of peripheral connections here and various internal things. But we'll come back to talk about this and also about the results in a few minutes, because something else has happened. Within the last couple of weeks, the evaluation board for the chip arrived. You can see it here. It's a pretty standard evaluation board, but it means that we can actually run things on the chip and give some demonstrations of what it does. Just looking at the board, you can see where the chip is, the Ethernet connection. There are a number of different kinds of special connections for video input from different kinds of cameras. The only one we had to hand, unfortunately, was a standard USB one, as you can see there. And the other connections are for power and a connection for a terminal, which is used initially to kick the system off. Over here is an SD card reader, and in it a card with Linux Ubuntu. So using this system, we thought we'd put together a couple of demos. Now, as I'm sure you're aware, when it comes to demonstrating something with neural networks, well, there's two different aspects to doing things with them. One aspect is training the network so that it has certain properties, and you end up in that case, after quite a lot of work typically, having looked at perhaps tens of thousands of examples of already classified images, you end up with a model expressed in a standard way, which is meant to be able to identify these kinds of images. We've actually done this with HISAOR, but it's something that's usually done offline, in the cloud or somewhere like that. The other thing that you do with the neural network is you use the model you've acquired as a result of somebody training something. You use that model, you feed it an object to be classified, and then you look at the classification probabilities that the model provides. So we picked a model for doing that. It's a system called YOLO, which stands for you only have to look once, which is rather nice. And this is actually the output of a satellite image that YOLO was asked to look at. And YOLO is a little bit unusual. It does two things. It both detects the location of an object in an image and then classifies it. So the kind of questions it asks, in a way, are there any things there? Where are they? And what are they? And in this case, YOLO came up with the answer. Oh, there are 3 ships. And in order for YOLO to do that, it took HISAOR less than 5 milliseconds to do that. But that's a very sort of standard example. So we thought we'd try something a bit more interesting. And instead of taking a pre-photographed image, just take a live feed from our USB camera. So in this image, again, we're using YOLO. And the slightly concerned looking person there is Barry. And we'll just kick this off. But as you can see, YOLO has already identified Barry as a person. And it's showing us, roughly speaking, where Barry is. This is really all an attribute of YOLO and not of HISAOR itself. But if we kick this off, you can see as Barry moves around, YOLO, this is Alex bringing in a bottle, and YOLO, it's being a bit, taking its time to identify it. It typically takes less than 5 milliseconds per frame. Hopefully it'll identify the cup. Oh, so it has. And it also identifies various other bottles in the background. Here's a cell phone. So YOLO gives both the location and the class of thing that's in that location. This is a book. It's actually quite a nice book by Roger Penrose called The Road to Reality. And for some reason that we haven't checked out, YOLO doesn't seem to want to recognize it. Perhaps it's because the book is so thick. But as you can see, this particular demo has not been made sophisticated in any way. It's exactly what we got when we just pointed our camera at the various objects that are there. In order to get the demo to work, in order to set it up, it was quite surprisingly simple. First of all, we had to take the YOLO model, which had already been trained, and use a tool, the Acuity IDE, to convert this to a version for use on HISAOR. On the evaluation, that was done on a PC, typically would be done offline, nothing to do with HISAOR itself. The evaluation board then, very simple to use. We connected the terminal and camera, powered up the evaluation board, used the terminal to identify where the operating system was, get it to start, log in to Linux over the internet, download and start the application, and things worked as expected. The reason for the exclamation marks, I need hardly explain to those of you who've been involved in developing new hardware. It worked pretty well out of the box. But going back to the chip, a couple of things that are quite important that you understand. This chip is not all our own work, by no means. It involves many IP cores from many different vendors. Some of the IP cores have space heritage already. All of them are from established vendors, and all have appropriate support software to allow them to be used with, for example, OpenVX or whatever. When the chip was being designed, those were parts of the criteria that any cores that were used had to meet. They had to have appropriate software, and they had to be very well supported, and as far as possible already in widespread use. HISAOR may be used on rockets, but we didn't want to get involved in rocket science in coming up with the processing involved. We wanted to be using high reliability, well-established IP cores. So, the question one then had to answer, what functionality would one like to have? What IP cores were available that might provide that functionality? And once you'd identify the cores that would be nice to have, a major question, of course, was how best to connect them together. Because with the multiplicity of devices on the chip, the contention for any buses that were there could well be very bad. One needs to find a way of connecting things that will minimize any contention for the bus and allow the highest possible throughput to be achieved. Another question, of course, always is on-chip versus off-chip memory. By leaving certain things off the chip, you can increase the amount of on-chip memory, and there are a whole lot of trade-offs there. But for a chip for use in space, clearly, for a chip in use in space, low power consumption, good radiation tolerance were clearly of major importance. And for this particular application area, we're looking for very fast image processing, both in relation to capturing the image and processing the image. Often the focus tends to be on processing the image. It's easy to forget that there can be quite a bit of processing involved in acquiring the image and converting it to an appropriate format. So that was one of the factors that was taken into account in the design of the chip. Fast neural network processing is essential, high numerical throughput, but also things have to be compatible with the existing software frameworks that are in use and widely available. And of course, for general purpose processing is important as well, and the ability to run an operating system such as Linux. On a satellite, there are many devices. One must be able to connect the chip to a wide range of different devices, as many as possible. So we looked around for, in the first place, something appropriate for the neural network type processing. And we came up with an IP core, which is very well supported, that has 8 GPUs, 8 neural network processors, high-speed cache, high-speed connectivity, and at its maximum clock rate of 1 gigahertz, can do 64 gigaflops and 12 teraops, 12 tera integer operations. For the main processing unit, for the central CPUs, once again we looked around and identified an IP core that was suitable, that had 4 ARM Cortex A9 CPUs, each with its own FPU and SIMD capabilities, with the caches you can see there, with high-speed connectivity, and with the with ARM's core side debug unit to allow what's going on to be monitored and corrected, and so on. Now, with this many things on a chip, 8 neural network processors, 8 GPUs, 4 ARM Cortex machines, there's every likelihood that they'll simply get in each other's way unless a lot of thought is put into the design of the on-chip bus. And I think that was one of the main challenges of the design of HISAOR, and the resulting on-chip bus looks a bit like this, and as you can see, is far from simple. So that's the kind of basic makeup, the main parts of HISAOR. But just going back to it again, as we said earlier, the central spine here shows the main computing components. Here we have the different kinds of interfaces provided, including some network interfaces, and so on. A lot of these have flight heritage already, these IP cores, and they're probably very familiar to many people, so it's probably no point in saying any more about them. And then on the chip you have some other devices like real-time clock, watchdog, various timers, and so on. And some on-chip memory. The design ended up with 64 kilobytes of ROM memory and 1 megabyte of on-chip RAM. The external memory connections are very fast and support DDR4 and also various kinds of flash and so on. Just looking at the central spine again, I haven't said anything much about the media processors, but the idea again is that the image coming in, you might have a JPEG image, you might have whatever, this will need to be converted to an appropriate format for processing by the GPUs and the neural network processors and so on. But at all events, that's the chip, and it works. The fact that it works, though, is due to a lot of people, not just OC technology. It was made possible by people in many organizations. We can't thank them all or recognize them all, but we do want in particular to thank Zhuhai Orbiter Aerospace Science and Technology Company, whose staff made a major contribution to both the design and implementation of HISAOR, and our thanks are also due to VeriSilicon, provided some of the main IP cores used and were helpful throughout the project, and to the Cronus Group for their work in relation to AI software. So we hope you found that interesting, and thank you for listening. And we hope as well that you find it interesting to try to play with the chip. Well, that's the wrong word, but certainly in the couple of weeks since the evaluation board has arrived here, we've had a certain amount of fun with it. So thank you again for listening, and any questions.